Hello everyone, welcome back to MP Coding, Linux Device Driver Development Series. In the last video, we discussed GPIO control. Today, we will look at GPIO interrupt handling. I will copy the request and free example folder from the last video, paste it once more, and then rename the folder to IRQ. I will also rename the source file and update the make file accordingly. Now, for interrupt handling APIs, we first need to include the linux/interrupt.h header file. Next, I will declare a global unsigned integer variable to store the IRQ number. I'll explain what this IRQ number means in a minute. Unsigned int IRQ_number. In the init function, after configuring the LED and button GPIOs, I will get the IRQ_number using the GPIO_ to _IRQ function. Here, we need to pass the GPIO pin that we want to configure as an external interrupt. In this case, I will use the button GPIO. This GPIO_ to _IRQ function in the Linux kernel is a legacy function used to map a global GPIO number to its corresponding interrupt request number. As mentioned in the last video, modern kernel code should use the descriptor-based GPIO API instead. I'll show how to do that later in this video. Next, we need to request the interrupt using the request_RQ function. This function takes several parameters. First one is IRQ number. Next one is the function to call when the IRQ occurs. Third one is the interrupt handling flags. Fourth is a name for the interrupt. Final one is a cookie passed to the handler, which is device ID. Let's first implement the ISR function. Static, then return type. What should be the return type? Let's look at it. This ISR function must be of type IRQ_handler_t. If we open the definition of the type, we can see function return type should be IRQ return_t and accept an int and a void pointer as parameters. Okay. Here set return type to IRQ return_t, and give a name for the function. I will give button_sr. The first parameter int is the IRQ number, and the second parameter void pointer is the device ID. Inside the function, first I will set the return value to IRQ_handled. If we look at the available other return values, IRQ_none means the interrupt was not from this device or was not handled. IRQ_handled means the interrupt was handled in this device. IRQ_wake_thread requests to wake the threaded interrupt handler. Here, we are simply indicating that the interrupt was handled by this device. Now, inside the button_sr function, I will print a message saying that an interrupt occurred on GPIO 20. Then I will toggle the GPIO LED. Using GPIO setValue function and pass the GPIO pin, then I will get the current GPIO value of the pin and toggle it. Now, let's update the request_RQ call. First, we pass the IRQ number. Then the button_sr handler. For the flags, I'll use IRQF_trigger_falling. You can use other trigger flags depending on your hardware and requirements. Next is the interrupt name. I'll use btn_IRQ_handler. Since we are not using a device ID, I'll pass null for the last parameter. This function returns 0 on success, so we must check the return value. If an error occurs, we'll print an error message and free the requested GPIOs. And return the -status value. Okay, we requested the IRQ number from the kernel. I will remove these GPIO set and get lines from the last example. We are now toggle the LED from the push button ISR. Finally, in the exit function, we must free the IRQ that we requested from the kernel. For that, we call free_IRQ and pass the IRQ number and the device ID, which is null in this case. Here one more thing. After requesting the IRQ from kernel, I will print the IRQ number, so we can check what is this number means. Alright, everything is ready. Now let's build the module and test it. Navigate to the source folder. Type make and hit enter. Okay, the build was successful. Before loading the module, let me show you the currently registered system interrupts. If we open the /proc/interrupts file, you can see many interrupts that are already registered for different system devices. Now, let's open the DMS buffer in another terminal and load the module using sudo insmod irq.ko. Here in the dmessage terminal, you can see that the IRQ number is 58, which means the IRQ was requested successfully. Now, if we check the /proc/interrupts file again, we can see a new entry added to the list with IRQ number 58. The label matches the name we provided in the code, and the interrupt controller shows pin control, BCM 2835, with GPIO number 20 configured for a falling edge trigger. Now, let's check if it works. When I press the button, you can see that the LED toggles, so the interrupt is working correctly. However, here we have a common problem with GPIO interrupts. If you look closely at this button press, you can see that it bounces. Because of this bouncing, the interrupt is triggered multiple times for a single press, and the LED ends up staying on, even though it should have turned off. This happens due to switch bouncing, also known as debounce issues. To overcome this problem, we need to implement a debounce timer, which is a common solution when handling GPIO interrupts. I'll show you how to do that next. Okay, now remove the module, sudo rm mod irq. Now, if we check the /proc/interrupts file again, you can see that IRQ number 58 has been removed from the list. Okay, let's implement the debounce timer. For that, first we need to include the linux/timer_types.h header file. I'll discuss kernel timers in more detail in the next video when we cover high-resolution timers. For this example, I'll just use a simple kernel timer. Now, let's implement the timer. First, I'll define the debounce delay as 20 milliseconds. I'll explain how this value works in a minute. Next, to store the last state of the button, I'll declare a global integer variable, static int last_button_state. Then, I'll declare a struct timer_list for the debounce timer. In the init function, after requesting the IRQ, we need to set up the debounce timer. For that, we use the timer_setup function. This function takes 3 parameters: a pointer to the timer, the callback function, and the timer flags. Let's first implement the timer callback function. I'll name this function debounce_timer_callback. This function must accept a pointer to a struct timer_list. Inside the callback, I'll read the current state of the button GPIO. Then I'll check whether the current button state is still the same as the last recorded button state. If it is, that means this is a valid button press, so I'll toggle the LED. Also, I will print a message, valid button press detected. Now in the button_isr function, remove this LED toggle. Here now we need to update the last_button_state variable and then start the debounce timer. These declarations should be before the button_isr function, so I will move these lines to up. Now to start or restart the timer, we use the mod_timer function. The first parameter is a pointer to the timer structure, which is debounce_timer. The second parameter is the expiration time, calculated as jiffies plus a delay converted from milliseconds to jiffies. Jiffies represents the current time in the Linux kernel, measured in internal timer ticks. Milliseconds_jiffies converts a delay value from milliseconds into kernel timer ticks. So it simply means, trigger this timer after 20 milliseconds from now. In our case, that's 20 milliseconds in the future, which gives the button enough time to settle and avoids false interrupts caused by bouncing. Finally, I almost forgot to update the init function. We must initialize the timer using timer_setup. The first parameter is the pointer to the timer structure. The second is the callback function. And the third is the flags. Here, I'll set the flags to 0, since we're not using any special options. Now, in the exit function, we need to remove the timer from the kernel. To do that, we use the del_timer_sync function and pass the reference to the debounce timer. What we are doing here is simple. When the button interrupt occurs, we only record the button state and start the debounce timer, which is set to 20 milliseconds. After 20 milliseconds, the timer callback function is executed. Inside the callback, we check whether the button state is still the same as it was 20 milliseconds earlier. If it is, we treat it as a valid button press and then toggle the LED. Okay, let's build the code. Type make and hit enter. Here we have an error, a funny one. This should be if, not int, so let me fix that quickly. Okay, let's build it again. This time, it builds successfully. Let's open dmessage buffer in this terminal. Now, load the module. Okay, the module is loaded. Now, let's check the button press. You can see that the button press works correctly, and the bouncing issue no longer occurs because of the 20 millisecond debounce timer. This is a common and effective way to handle GPIO push-button interrupts. You can change the debounce delay based on the requirements of your application. In most cases, 20 milliseconds is a safe value. Now, let's look at how to correctly handle GPIO interrupts. Up to now, we have been using the old legacy GPIO API. However, the current best practice for handling GPIOs and GPIO interrupts in a Linux kernel module is to use the GPIO descriptor-based API. I have updated the code to demonstrate this properly. If you've been following this series, you already saw in the previous video how we use the GPIO descriptor method, and here we extend that approach to interrupt handling and debouncing. To make comparison easy, I defined this macro use_descriptor_API. Using this macro, we can switch between the legacy GPIO API and the descriptor-based API at compile time. When the descriptor API is enabled, we include Linux/GPIO/consumer.h. Otherwise, we fall back to the legacy Linux/GPIO.h. In descriptor mode, I declare two static global pointers. One for the LED GPIO descriptor, one for the button GPIO descriptor. These are declared as struct GPIO_desk pointers, just like in the previous video. Inside the init function, we convert the GPIO numbers to descriptors using GPIO to desk function for both LED and button. Once we get the descriptors, we configure the LED as an output using GPIOD direction output, the button as an input using GPIOD direction input. This replaces the legacy GPIO request and GPIO direction calls. When using the descriptor API, we do not use GPIO to IRQ. Instead, we use GPIOD to IRQ and pass the button descriptor pointer. This converts the GPIO descriptor directly into an IRQ number, which is the recommended and correct method in modern kernel code. In other GPIO set and get methods also should be GPIOD calls, so you can see the source code how it's done. Apart from these changes, the rest of the logic are same as before. One important thing to note is that GPIO freeing functions are only required when using the legacy API. When using the descriptor-based API, GPIO resource management is handled by the kernel. Okay, let's build the code. The build was successful. Now, let's load the module. You can see the output in the terminal, and the IRQ number is 58. If we look at the /proc/interrupts file, you can see that the interrupt has been added to the list. The button press behaves the same as before, including the debounce handling. If we remove the module and check the /proc/interrupts file again, you can see that IRQ number 58 is gone. So, this is how we implement GPIO interrupt handling using the descriptor-based API. We have already covered the debouncing example. Now, let's quickly see how the top half and bottom half work in an interrupt handler. In Linux kernel development, interrupt handling is divided into two parts, the top half and the bottom half. The top half is the interrupt service routine, or ISR. It runs immediately when the interrupt occurs and must execute as quickly as possible. Its job is usually limited to acknowledging the interrupt, saving minimal state, and scheduling further work. The bottom half handles the rest of the processing that does not need to run immediately. This part runs later, outside the interrupt context, so it can safely perform longer operations without blocking the CPU. In simple terms, top half, handle the interrupt quickly. Bottom half, do the remaining work later. This split helps keep the system responsive and stable, even when interrupts occur frequently. I have already written the code for this example, and I'm using the legacy GPIO method here. As you already know, it's easy to update this code to the descriptor-based API, so I won't repeat that part again. Okay, let's look at the code. To keep things simple, I'm not using a debounce timer in this example. So, I removed the Linux/timer_types.h header file and instead added Linux/workqueue.h and Linux/delay.h. These headers are required for implementing the bottom half using workqueues. Next, I added a new work_struct from the workqueue API, and I named it button_work. This structure represents the bottom half task. In the init function, I initialize this work structure using the init_work macro. Here, we need to pass button_work structure and the function that will act as the work handler. Now, let's see what this button work handler does. This function represents the bottom half of the button interrupt handler. Inside this function, I simply simulate a slow operation by sleeping for 1 second, and then I toggle the LED. This kind of operation should never be done in the top half, because it takes too long. In the top half, which is the actual ISR, I do only one thing. I schedule the bottom half work using the schedule_work function, and I pass the pointer to the button_work structure. So the flow is: interrupt occurs. Top half runs quickly and schedules the work. Bottom half runs later and performs the slow operation. Finally, in the exit function, we must make sure that no pending work is still running. To do that, we call cancel_work_sync, which safely cancels any scheduled work before unloading the module. Okay, That's all for this example. Now, let's build the code. Okay, the build was successful. Now, let's load the module. The module loaded successfully. When I press the button, you can see that the ISR is triggered immediately, and we can see that in the D message output. However, the LED toggles after a 1-second delay, which means the bottom half work is scheduled and executed correctly. Okay, that's it for today's video. In the next video, we'll discuss high-resolution timers, so stay tuned. If you found this video helpful, please like and subscribe to the channel. See you in the next video.